Welcome to Shanti-Peace for Mathematics. In my previous videos, we have talked about the spectrum of different operators. For example, we have seen the spectrums, which is nothing but the set of all scalars such that t minus lambda I is not invertible, where t is belongs to BL of H, which is a set of all bounded linear operator defined on Hilbert space H. And then we have seen another two types of a spectrum, the eigenspectrum and approximate eigenspectrum. We have talked about the spectrum of a normal operator, self-adjoint operator. We have also talked about the numerical range of an operator and various other properties of that. Now in this lecture we are going to discuss another class of uh, operator which is known as a compact operator. You already have heard this name compact in your topology course, in which we have defined a compact set if every family has finite subcover. Sequentially compact definition we already have defined as every sequence has convergence subsequent. Now if you can see this definition, and based on that definition we have generalized the definition of a compact operator. So let us discuss the definition of a compact operator. It says that let H be a Hilbert space. T is a map from H to H be a linear. That means I can say it is a linear operator. T is said to be compact. Every bounded sequence Xn in H, if you have Txn, T of Xn is also a sequence, has convergence subsequence. So if this T satisfies this condition, then this linear operator T is known as a compact operator. We'll see once again a definition of this compact operator. It says that every bounded sequence in H, if T of Xn has convergence subsequence, so you are taking a sequence in domain and you are looking of its image have the convergence subsequence in codomain, then we can say that it is a compact operator. A compact set is like that every sequence in that space has convergence subsequence. Here it's slightly different, so it is a function. Now let us see some examples of this compact operator. So if I have a linear map T which is from K to K, where we consider this K is a scalar field, either R or C, then any bounded linear map is always compact operator. So what is my claim is every bounded linear map P from K to K, where K is a scalar field, is compact. And this statement is very easily seen. So to prove this statement, I need to have one bounded sequence in K and need to see what is the image of that sequence. Will it have a convergence subsequence? So to see this, let us consider Xn be a bounded sequence in K. Therefore, T of Xn is also a bounded sequence in its codomain because T is bounded. Since T is bounded, T of K is also bounded. And just recall one of the results which you have studied in your undergraduates is regarding a Bolzano-Weierstrass theorem, which tells you that every bounded sequence has convergence subsequence. Now, if I apply this Bolzano-Weierstrass theorems on this T of Xn, because it is a bounded in K, so by this Bolzano-Weierstrass theorem, it tells that every bounded real sequence has convergence subsequence. So due to that, we can say that this T of xn has a conversion subsequent. So it's proved that T is compact. Now here what we have did in this, so we make this statement that every bounded linear operator defined over k to k, that means defined, it is operator from k to k, it's always compact. Bounded linear operator defined on this two. We can have more general statement than this. Why it is k only, a scalar field, but the result is also true for k power n. Let me state that result, that every bounded linear operator T from Kn to Kn is compact. And this is also easily seen using the Bolzano-Vasquez theorem, which is true also for Kn, that is R power n or C power n. Now, after doing this, let us move forward and let us consider one theorem based on this compact operator. So let H be a Hilbert space and T is from H to H be a compact linear transformation, then prove that T is bounded. So it is the same result as we have studied. If it is compact, a set is compact, then it is always a bounded set. So here, if the map which is a compact linear operator, then it is bounded. Now let us try to prove this statement. Or given that T is compact, we shall show that T is bounded. If I can apply the definition of boundedness, then it is sufficient to show that there exists alpha greater than 0 such that norm of Tx is less than or equal to alpha for every x belongs to H and norm of x is less than or equal to 1. This is our objective. Suppose T is not bounded. So suppose that by contradiction we are starting with T is not bounded. If it is not bounded, then this statement, it will be contradict. If I make the contradict statement of this, instead of there exists alpha, we should have for each beta greater than 0, for every x belongs to H, so therefore instead of that there exists some x beta belongs to H with norm of x beta is less than or equal to 1 such that instead of having norm of Tx is less than or equal to alpha, we can have norm of Tx beta is greater than. Now what I will take in particular, I'll take beta equal to 1 because this statement is true for every beta greater than 0. So in particular beta equal to 1, we can have there exists some x1 belongs to H with norm of x1 is less than or equal to 1 such that norm of T x1 is greater than 1. Now instead of beta equal to 1, I will just take now another quantity as beta. So by taking beta is equal to 1 plus norm of T x1, then there exists 2 belongs to H with norm of x2 is less than or equal to 1 such that norm of Tx2 is greater than beta, but we have taken beta is this, so it is 1 plus norm of Tx1. Now by taking beta is equal to, now this statement is true for every beta, so I am just taking another value of beta as a maximum 1 plus maximum of norm of Tx1 comma norm of Tx2. So this two values, that is this and this value we have. So by having this two values as greater than, we can have that exist x3 belongs to H such that norm of x3 is less than or equal to 1, norm of Tx3 is greater than 1 plus maximum of norm of Tx1, norm of Tx2. And if you continuing like this one, so in the next time you will just take that beta is equal to 1 plus maximum of Tx1, norm of Tx2, norm of Tx3. Then if you go in that manner, so continuing this way, we get sequence of numbers, that is sequence of elements, that is x1, x2, so on xn, such that all of them having the norm which are less than or equal to 1, where j is running from 1 to n, and norm of pxn is greater than 1 plus maximum of norm of px1, norm of px2 up to norm of pxn. Here it should be norm of pxn minus 1 will be there. So this is actually, you will have norm of pxn minus 1. Now this will suggest you that for any n greater than n less than m, you will have norm of pxm is greater than 1 plus norm of pxn. Because this is further, I can say that this is less than 1 plus any of this value. So if your n is bigger, then I can say that norm of pxn is greater than 1 plus norm of pxi, where xi is running from 1 to up to n minus 1. So if you can go further, if your m is bigger, then you will have a norm of pxm is greater than 1 plus norm of px. So this will gives you norm of pxn minus norm of pxn is greater than 1. But this will suggest you that norm of pxn minus xm will be same as norm of txn minus txm, because of t is linear, and that quantity is greater than or equal to norm of txm minus norm of txm, and it suggests that this will be greater than 1. So what is that suggests? That this sequence t of xn is not a Cauchy sequence. Since it is not Cauchy, that means after some times a difference between two element in that sequence is bigger than 1. It suggests that after some times the difference between these two terms is bigger than 1. Any two terms is bigger than 1. So it is not Cauchy sequence, and therefore I can say that this t of xn does not have conversion subsequence, hence is not compact. It's contradiction with the fact that t is compact, and therefore we can say that t is. So here we have proved that t is compact implies t is bounded. Obviously one can ask the question, is converse of this result is true? We already have proved for some particular case that thing. That means if you have t which is from kn to kn is bounded linear operator, then that will imply t is compact. That is true. But the converse of this result is not true. So obviously for finite dimensional space, the result is true. So we need to consider an example for infinite dimensional space. So let H be a Hilbert space with a dimension of H is infinity. Let us also consider this U1, U2 up to so on, a orthonormal set of H. Since it is orthonormal, we can say that norm of un is equal to 1 for every n. I can say that the sequence which we have created from this un is a bounded sequence. Now let us consider identity operator, that is h to h, as I of x is equal to x for every x belongs to h. You can see that this I is bounded linear operator. But our objective is to claim that this I is not a compact operator. So if I want to prove that it is not compact operator, I need to have I of un does not have any conversion subsequence. So to see this, we'll start with norm of I un minus I um. If I consider n is not equal to m, I'm starting with this. Since it is identity map, so it is norm of un minus um. I'm taking a square both side. So this is un um. By expanding this norm as an inner product, we can have it is u and un minus un um minus un plus um. Now you can just see that this un is an orthonormal sequence. So that's why this will gives me 1. Since n and m are not same, this two quantity will become 0 and this is also 1. So that's why it will be 2. So we can have norm of I n minus I m is square root of 2. That means the difference of this two point in that sequence after some times it is always remain constant. So I can say that the I un does not have conversion. I is a bounded linear operator, but bounded sequence does not have a convergence subsequence. So therefore I can say that I is not compact. Hence the bounded operator does not imply that it is compact. Now let us move forward with some more results on this compact operator. So let's have this result. Let H be a Hilbert space and T belongs to BL of H. If the dimension of a range space of T is finite, that means a rank of this operator T is a finite, then T is compact. So this result is also gives you regarding in which situation the bounded linear operator will become a compact operator. So we already have seen that if T isn't defined for finite dimensional space, then it is compact. But this is also one more result. If H is infinite dimensional space, but the range space of this T is a finite dimension, then also we can say that T is compact. Now to see the proof of this, let us suppose that dimension of range space of T is M. Let u1, u2 up to um be a orthonormal basis of range space of T. Now let us define phi, which is RT2. That means let us define this map range space of T from k power m with the 2 norm. That means I am defining a map from RT to phi. Phi of x is equal to inner product of x u1, inner product of x u2 up to so on x un. Now one can observe very well that this phi is a linear operator that is easily checked because phi of x plus y, if x and y belongs to the range space of T, then by definition of inner product we can separate out this. So I can write down this phi of x plus phi of y. You can verify this. Also you can verify that phi of alpha x is alpha times phi of x, and both this quantity is true for every xy belongs to a range space of T and alpha belongs to K. Therefore I can say that phi is a linear map. Also let us observe what is the norm of phi of x. So a phi of x is in codomain, so there is a norm is a 2 norm is there, so that's why it is I can write 2 norm of that. So it is a 2 norm of that vector which we have. It is a x u1 x u2 up to so on x un, and it is a 2 norm of that, which we can say it is summation I running from 1 to n, mode of x ui whole raised to 1 by 2. You can observe that this quantity is nothing but the norm of x. Hence, this phi is also an isometry. And it is clear that it is onto. This you can verify. Therefore, your phi, which we can have it is a linear, isometry, and onto. Our objective is to prove that T is a compact operator. So for that I need to start with the sequence xn will be a bounded sequence. Since this bounded operator of xn also bounded, and since phi is an isometry, the phi of T of xn is also bounded. Norm of this quantity will be same as norm of this. This phi of T of xn is bounded in power n. Now there is a bounded sequence in k power n. So I can apply the Bolzano-Weierstrass property to show that this sequence, this bounded sequence has convergence subsequence. Therefore, by Bolzano-Weierstrass property k power n, phi of T of xn has a convergent subsequence. Let us say that convergence subsequence is phi of T of xn1. Now let us observe what is this quantity phi of T of x1, in which this T of x1 is actually a subsequence of T of xn. That here 1 a convergent subsequence of T of xn, and therefore T is compact. So here we have proved that if your range space, finite dimensional space, then your bounded linear operator will be a compact. Obviously, if H is a finite dimensional space, then bounded linear operator is compact. If H is finite dimensional space, a range space is also finite dimensional, so therefore T is compact. This we can write as a remark that if a dimension of H is finite and T is belongs to BL of H, BL of H stands for a set of all bounded linear operator defined on H, and T is compact. This dimension is finite, a range space is also finite dimensional space. So therefore T is compact by previous result. One more note we can write here is, if you have the identity operator Hilbert space, if you want that it is compact, then it is if and only if H should be of finite dimensional space. Identity map defined on a Hilbert space, if you want that a compact, then the Hilbert space must be of a finite dimension. Result is another results which support that when the bounded linear operator become a compact. So this result is about to saying that if you have a sequence of compact operator, then its limit is also a compact operator. So that statement is said like this, that H be a Hilbert space and Tn is a sequence of a compact operator such that Tn is converged to T in bounded linear space of bounded linear operators. This limit of that sequence of compact operator is also compact. So that means limit is preserve the compactness. See the proof of this. To prove that T is compact, so I have to start with the bounded sequence in H. So suppose that N is a bounded sequence. By definition, there exists alpha greater than 0 such that norm of xn is less than alpha for every n. I have given that this sequence Tn, which is a sequence of a compact operator. So I can say that T1 is a compact. So as T1 is compact, is a bounded sequence. So I can say that T1 of xn is a convergent subsequence. Let's say that convergent subsequence is T1 of xn1. This xn1 is also a subsequence of xn, and since xn is bounded, xn1 is also a bounded sequence. As xn1 is a subsequence of a bounded sequence, xn1 is also bounded. Since it is a bounded, T2 is compact. This will imply that T2x and 1 has convergent subsequence. Let us say that convergent subsequence is T2 of x and 2. Now as x and 2 is a subsequence of x and 1, which is a bounded, so therefore I can say that T of x2 is sequence of 1, and T1 of x and 1 is convergent. Therefore, T1 of x and 2 is also convergent. This sequence is also convergent. And if you continue in this manner, that means the next time you can have a subsequence T3x and 3 will be convergent, and x and 3 is subsequence of x and 1. So I can have the same scenario. And so continuing in this manner, we get a convergent subsequence k, x and k such that x and k is convergent for all, x and j is convergent for all j running from 1 to up to k, and therefore Tn, x and n convergent for each n. Now I will start with T of xkk minus T of xmm. So I am starting with this subsequence. Now adding and subtracting some terms here. We just observe that this is T of xkk minus T of Tn of xkk. So that's, I can write less than or equal to. So I am subtracting this term and adding that term Tn xkk, and then subtracting Tn xmm. Here I'll subtract this term, so I'll need to add this, and then last term is T of xmm, and by applying a triangular inequality we get this. Now here xk k is same, so I can take this as a definition of pointwise subtraction. Here I'm applying the Tn is linear, and here also the same thing. So therefore by doing this, norm of T x k k minus T of x m is less than or equal to norm of T minus Tn norm of x k k. that comes from that. You can just see that t minus t of t minus tn of xkk, and then applying the things that this is. So that's why this is less than or equal to this one plus norm of tn x kk minus tn x mm, which is as it is. You have here the second term. In the last term also applying the same situation. So that is plus norm of t minus tn norm of x mm. This quantity is less than alpha. This quantity is also less than alpha. So this is less than alpha times norm of t minus tn, which comes also the same term comes here. So that is 2 times alpha times norm of t minus tn plus this quantity, that is norm of tn xkk minus tn xmm, norm of this is there. Now this quantity is already tending to 0 because we have given tn is tends to t. The first quantity is tending to 0 and second quantity is tending to 0 due to we have this tn xn n is a conversion substitute, is a conversion. So therefore this is also tends to 0, and hence we can say that t xn k is a Cauchy sequence in H, and H in a Hilbert space. As H is a Hilbert space, T of xkk is convergent. What is T of xkk is actually a subsequence of txn. So therefore I can say that subsequence xkk of txn is convergent, and therefore T is compact. So if you have a sequence of a compact operator, and if that converges to some limit in BL of H, then that limit is also a compact operator. One more results we are discussing now, it's about the adjoint. Obvious question one can ask that if T is compact operator, will it be its adjoint is also a compact operator? So the answer is true. It means that H be a Hilbert space, T belongs to BL of H is compact, then prove that T star is also compact. Now to prove this statement, start with the one bounded sequence in H, because I have to prove that T star is compact. So let Xn be a bounded sequence in H. Therefore, there exists alpha greater than 0 such that norm of Txn is less than or equal to alpha for every n. This is true. As T is belongs to BL of H, this will imply T star is also belongs to BL of H. This will imply T star is a bounded operator. Since it is a bounded operator and the sequence is bounded, so I can say that therefore T star of Xn is a bounded sequence. Now let us consider n, this value T star of Xn, the same value which we have here, for every n running from 1 to up to so on. What is given is as T is compact, this Yn has conversion sequence subsequence, because this is bounded, so this Yn should have conversion subsequence. So I can say that Yn has conversion subsequence. Let us say that conversion subsequence is T of y and j. Therefore, j and k belongs to n. I'll start with that. Again, I'm starting with the Cauchy sequence, that is t star of xn j minus t star of xn k. Definition of this norm, this is nothing but the inner product of t star of x and j minus t star of x and k, t star of x and j minus t star of x and k. I'm using this two quantity as y. This is y and k, so this is y and j minus y and k, t star of x and j minus x and k. Applying the definition of adjoint, you can have this t star I can take on this side, so this is t of y and j minus y and k, x and j minus x and k. But t of this will gives you, and here there is modulus, so by squares inequality we can say that this is less than or equal to norm of t of y and j minus t of y and k, norm of x and j minus x and k. But this t, y and j is stay as it is. Xn is a bounded sequence, so this is less than or equal to 2 times, because this is less than or equal to this plus this, so that's why it is, I can say that, therefore norm of t star x and j minus norm of t star x and k square is less than or equal to 2 times alpha norm of t y and j minus t y and k. You see that this is 2 times alpha and that quantity as this. But t y and j minus t y and k, due to that, as it is a conversion subsequence which we have, so that's why this is also Cauchy, and since it is a Cauchy, it will tends to 0. I can say that t star x and j is a Cauchy sequence. Hence, we can say that t star of j is conversion sequence because H is a Hilbert space, complete space is there. So Cauchy sequence will become conversion sequence. And what is T star x and j is a subsequence of T star x n, so that's why T star is compact. So what we have proved here it is, if T is compact, then its adjoint is also compact. Let's have one more and last result, which tells you that let H be a Hilbert space, and this result is talking about the algebra of compact operators, which that says that if you have a two compact operator, s plus t and alpha times s is compact, where alpha is belongs to k, that is a scalar. And if s is compact and t is belongs to bl of h, then st and ts are compact. And it tells you that this is the two-side ideal, so that if you can have set of all compact operator in one set, and then a set of all compact operator is two-side ideal of BL of H. Prove this statement. If I want to prove that S plus T is compact, I have to start with a bounded sequence in H. So let be a bounded sequence. S is compact and T is compact given that. So as S and T are compact, S of xn has a convergent subsequence, say Sxn j, and T is also compact, so I can say that therefore T of xn has a convergent subsequence xn k. Since S of xn is convergent and S of xn k is a subsequence of S, X and J, then X and K is a convergent. So S, X and J is convergent, this is also convergent, the sum of two convergent sequences is also convergent, so therefore I can say that S, X and K plus T, X and K is convergent in it. Therefore S plus T of X and K is convergent and therefore S plus T is compact. Now similarly you can prove that alpha times, so for that let us have xn is bounded, is compact, so S of xn is has convergent subsequence, that convergent subsequence is xnj, and therefore alpha times xnj, if I multiply by constant, the nature of this sequence will be same, it is convergent for all alpha belongs to K, and therefore alpha S is a compact. Now secondly we need to prove this is a side and right side ideal, two side ideal. So to prove that one, I am again taking a sequence of xn be bounded. As T is bounded, which we have given, you can see that T is bounded linear operator, so T is bounded operator, and xn is a bounded sequence, so T of xn is bounded. As S is a compact, S of T of xn has convergent subsequence, and therefore ST is compact. Now if I want to prove that TS is compact, then let us consider xn is a bounded sequence. Since S is compact, S of xn has a convergent subsequence. Say that convergent subsequence is S, X and J. And as T belongs to BL of H, this will imply T is continuous. T is continuous of X and J is convergent. Because if T is continuous, Xn converges to X, which implies that T of Xn is converged to T of X. So this, if I apply T on this, it is automatically convergent. So that's prove that TS is also convergent. So this statement, it gives you that you can have Kn, K of H, some script K of H is the set of all compact operator defined on H, then you can say that K of H is two-sided ideal BL of H. So lastly, I want to say that if T is belongs to the scale of H, that means if T is a compact operator, we can say about T inverse whether it is a compact operator or not. See, if T is a compact operator, therefore T inverse is automatically bounded operator, and we know that it is a bounded operator. The dimension of H should be finite. So this statement is actually true if and only if dimension of H is finite. So I'm repeating again, if you have a T which is a compact operator, then T inverse is bounded if and only if dimension of H is finite. Now to see this one, it's T is compact and T has inverse, so that inverse is exists. T inverse is equal to identity. Now if I apply this result previously, which we have here, we have S is a compact and T is BL of H. So ST is a compact and TS is also compact. So as per that, we can say that T inverse is bounded operator, but T is belongs to this KH. So that's why this is a compact operator. And we already have mentioned that identity is a compact operator if and only if dimension of H should be finite. So this is my last result for this lecture. Let us recall what we have did till now for this compact operator. So we have defined a compact operator which tells you that if you have a sequence which is a bounded, then T of xn has a convergent subsequence, then T is called the compact operator. We have seen that in finite dimensional spaces, every bounded linear operator is compact. T is compact, then it will always implies T is bounded. The converse is not true. We have to consider an infinite dimensional space, then the converse is true. Another way a converse is true, that means if T is bounded linear operator and the dimension of a range space of T is finite, then this will imply T is compact. The next result which we have discussed is if you have a Tn which is a sequence of a compact operator, and if Tn is converse to T, then T is also a compact operator. So another result we have discussed that if T is compact operator, then T star, that its adjoint, is also a compact operator. Lastly, we have seen that if S and T both of them are a compact operator, then S plus T is also compact operator. Alpha S is also a compact operator. That means if I can have this KH, which is a set of all compact operator defined on H, then it will become a vector space. So this is a vector space. Furthermore, we are saying that if T is belongs to BL of H and S belongs to this K of H, which is a set of all compact operator, then TS and ST are compact operator. Lastly, we have seen that if T is belongs to bounded operator which is invertible, and if you want that T inverse is exists, then H should be finite dimensional space. So if T is a compact operator and if you want that T inverse is bounded, then H has to be a finite dimensional space. So that's it for this video. If you like this video, please do subscribe the channel. Thank you very much. See you in next video. Till then, bye bye. Sayonara.